two things that we're going to talk about today. The first is going to be piecewise functions, and the second is going to be the step functions, which includes the greatest integer function, one of those functions on your pink sheet. So if you're like, I don't really understand the greatest integer function at all, we're going to talk about that, and then you'll be able to fill out your pink sheet from there. Okay. Piecewise function, I want you to think about the name of that type of function. First of all, it's a function, so it has to pass the vertical line test. Second, piecewise, it's pieces of different graphs put together, but then it still passes a vertical line test. So here's an example of what a piecewise function can look like. And remember what I said, it's pieces of functions. So I have two separate functions, okay, two different lines, and then behind each equation, there's a comma, and it tells me about when that function is valid. For what x's I should graph that function. So for the first function, it's for x's that are less than or equal to -4. If you're thinking about the coordinate plane, in what direction is less than -4? To the left of -4. Okay, so to the left of -4, and because it has the or equals to, including -4, you would graph the line -1/2 x minus 6. Okay, so I'm going to jot down here. Left of x equals -4 includes x equals -4. In the second graph, you're supposed to graph x is for when x is greater than -4. So in what direction would be greater than -4? To the right. And are you supposed to include -4? No, because it doesn't have the or equals to. So this graph is going to show up right of x equals -4. Do not include x equals -4. So it's like you're breaking up your coordinate plane, and on one side or one part you graph one function over there, and on the other side or other part of your graph you're going to graph a whole new function. Okay? The includes and does not include, you can think about that with our intervals, interval notation, brackets, parentheses. That kind of goes along with our less than or equal to, greater than or equal to, right? So, but when you're thinking about a graph, if it includes it, how would you mark that on a graph? Closed circle, Campbell says. If it doesn't include that number, you would mark it as an open circle. So that's going to be like a big thing for us to think about. If it has or equals to, it's going to be closed at -4. If it has no or equals to sign, it's going to be an open circle at x equals -4. So we're going to actually graph this one. This one's pretty easy because they're both lines, and then we'll do another one together. So this is our first piecewise function. It's the same one I had on the previous slide. And the way I set it up is I really just do one at a time. So I'm going to focus on -1/2 x minus 6. I have found that a lot of students find success in piecewise functions if they just make table of values. So when you're making the table of values, you have to think about that restriction for x's that are less than or equal to -4. What kinds of numbers work? Give me a number that works for x. -4. Is -3 less than -4? That's greater, so we gotta go to -5, right? So we gotta do -4, -5, -6, things that are less than to the left of. And remember, at -4, it's going to be a closed circle because it has the or equals to. Okay? So then you just plug in and evaluate. -1/2 times -4 is 2, minus 6 is -4. I'm going to skip the -5 because I'm going to get a decimal. Not that I couldn't do it, but I'm just going to jump down to -6 because I really only need 2 points to make a line. -1/2 times -6 is 3. 3 minus 6 is -3. What must -5 be? -3.5. Okay, it's got a slope of -1/2, right? So they're going down. Okay. And I can plot those points. Make a little table or make a coordinate plane. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, something like that. And I'm going to go 4 to the left and 4 down. And I got a closed circle. I could go 5 to the left and 3.5 down. And 6 to the left and 3 down. I really only needed 2 points for a line. Okay, an overkill here. And everything was to the left of the -4, so I want to start there and draw my line left. So that graph only appears on the left side of my coordinate plane. Left of -4. Are we okay with what I did? Okay. Now I've got to do the other function. So that's x plus 5. I'm going to make a new table. If it's a line, you really only need 2 points. Okay? But you can put extra points if you want for a better graph. What points work? 5 would work. 0 would work. 1. What's the last number that works? Oh, -3 is the last number that works? -3.999999999, which is really close to what? -4. So let's put -4 in our table. Even though it doesn't work, what kind of graph will we draw? An open circle at -4. And then we can include any of those numbers you guys said. 5, 1, -3. Okay. Any other number would have been okay. But no matter what, you should include the boundary number in your table because, like, was it Noah that said -3.9999? Okay. You need to butt up into that point so that you get all the points. If you just start at -3, you're missing a chunk of points in between -4 and -3. So you want to do that point, but mark it as open. Well, these are easy to evaluate, 1 and 2. So I'm going to go 4 to the left and up 1. That's going to be open. 3 to the left and up 2. Now that's included, so that's going to be closed like a regular. And my line is going to be solid because everything works except for -4. So the -4 is just an open circle. And look, you have 2 pieces of graphs on the same graph. It's a piecewise function. If you want to check to see if your graph is kind of making sense, it should pass a vertical line test. So I guess the one point of concern would be the vertical line x equals -4. But because we have one closed and one open, it passes the vertical line test. It's still a piecewise function. You can also have some piecewise functions where, like, the 2 parts, the open and closed circles might be at the same point. So then it just looks like a closed circle and a continuous graph. That would be fine. So the closed circle will always override the open circle. It's a point. Real quick, I just want to show you another example. This one is just a little bit more complex for a couple of reasons. It has 3 parts, and it has a quadratic in it. So when I'm thinking about my graph, I should have 2 parts that look like straight lines, and I should have 1 part. Whether it looks like a full parabola or not really depends on what the interval is, but it should be a curve of some kind. It shouldn't be a straight line anymore. Okay? So if I were to set this one up, I would just break them up into 3 parts. Okay? Make a table. If it's a line, you really only need 2 points. So look at your interval, x is less than 0. I'm going to include 0, but mark it as an open circle because it doesn't have or equals to, and then any number that's less than 0. -1. Evaluate, and I can graph. It shouldn't really be very hard. 0, 1 is open, -1, 0 is closed, and we're going all the way to the left because it's less than 0. What's always difficult about piecewise is that you got to keep track of everything, but you just need to kind of break it up into chunks. Do one function, then another, then another. When I get to the quadratic, and if you have more than one function, notice that this interval goes from 0 to 3. So I am going to include those endpoints, 0 and 3, in my table. 0 has the or equals to, so that's going to be closed. 3 does not, so that's going to be open. And then if it were a line, I would probably just do those two and connect them. Since it's quadratic, I might pick some more points in between. So I'm just going to do 1 and 2. And then evaluate. That would be 4, 1, 0, and 1. And I can plot. So you're plugging in those x values and evaluating. Always think about those endpoints. Are they going to be closed or open? Right? That's important so that you'll pass the vertical line test. 0, 4 is closed. 3, 1 is open. The only point that's open on a graph is that point that's not included in the interval. Okay, so everything else should be a closed point or a solid curve or a solid line. And then I can finish up with that last equation, 3x minus 2. So I notice this one is linear. I'm going to start it at 3, which is going to be closed, and then just choose one other point. I'll choose 4. So it fits in the interval. It's greater than 3. Evaluate. I should get 7 and 10. So 3 to the right and 7 up is closed. 4 to the right and 10 up. What's that? Questions, thoughts? Now, I can look at that and it's going to pass the vertical line test, so I'm confident that I have things in the right sections. It's just a matter of did I do my tables correctly. Maybe have any questions about the piecewise that they want to ask? You should have time to work on a piecewise in class today, and that'll be nice because we can kind of troubleshoot for about where to start. All right, we have one other thing we want to talk about before you get started on your homework assignment, and those are the step functions. Okay. So step functions are called step functions because they look like stairs or steps. And some people maybe filled out the pink sheet because you looked in the back of the textbook and you thought, well, this is a strange function when you got to greatest integer. Okay, and now you're thinking about it and you're like, yeah, it does look like steps. Okay. There are multiple types of step functions. Okay, greatest integer function is one of them. Okay. And greatest integer function, the function notation looks like this, f of x equals, and then we would read that as the greatest integer of x, like you would read the absolute value of x. It's the greatest integer of x. It's basically like a double bracket. So I usually draw a bracket and then line. And I would definitely write down what's in quotes there. That's going to help you on your homework assignment. How do you do the greatest integer function? What does it mean mathematically? you can put functions into the greatest integer function, and the output is the greatest integer that is less than or equal to that value. The greatest integer that is less than or equal to what you put into the function. So a couple of things, or one thing that we have to talk about before we do any examples there are, what are integers? What's that? Whole numbers. Okay, whole numbers is a subset of integers. Integers include more numbers than the whole numbers. What do they include? The negatives, right? Okay, so I often call the integers nice numbers. They're numbers without decimals or fractions, right? 1, 2, 3, 0, -1, -2, -3. Those are integers. Okay? So when you do the greatest integer function, your outputs have to be nice numbers. Your outputs will be an integer. There are no decimals or fractions in your answers. Okay? So we're going to do, you could do a table of values. I think on your homework it asks you to do some function notation. So I'm modeling that for you for your homework. We're going to evaluate these in the greatest integer function. Okay? So if it's f of 0, and f of x is the greatest integer of x, that means what's the greatest integer that's less than or equal to 0? The answer is 0. It's equal to, right? Okay, so that would be a point on our graph, 0, 0. All right, what is the greatest integer that is less than or equal to 0.5? Also 0. It's not 0.5 because that's not an integer, and it can't be 1 because that's greater than, not less than, so we got to go back down to 0. So 0.5 is also 0. Think about all these points in between 0 and 1. 0.2, 0.3, 0.47, 0.99999. The greatest integer of all of those is 0. It always goes back to 0. So this is why we're forming what looks like a step. But what happens when you put in 1? It goes up to 1. So 1 is not a point at 0. It has an open circle on the end. Okay, so it's closed everything to 1, open circle. And then Elena says, when we put in f of 1, the greatest integer of 1, so the greatest integer less than or equal to 1 is 1, then that's a new point. Right 1, up 1. What's the greatest integer of 1.2? 1. We can't say 2 because that's more than 1.2. What's the closest integer that's underneath 1.2? That's 1. Okay. So then we do that thing again where all the numbers in between 1 and 2, 1.1, 1.2, 1.4, 1.99999, their greatest integers are all 1. They all go back to 1. It has to be less than or equal to. Okay? So they all go back to 1, but then when you get to 2, the greatest integer of 2 is 2. So this is not a point because it jumps up to 2 at that moment. And all the decimals of 2 go back to 2 until you get to the next integer, 3. And so you're building the steps. Emily.
So we don't even need to graph like f of 1.2?
Yeah, you don't really need to. It's there.
Oh.
Right? But it's there along with infinitely many other points. 1.19, 1.18, so on and so on, right? I can't even. Yeah. Yeah, so like this one will keep going. These are this is 1, This is zeros, these are ones, these are twos, and then it'll go 3, so on and so on. And then down here, it has to pass the vertical line test, so this is going to be your open circle, and then a closed circle. So if you're thinking about that like f of negative 0.5, what's the greatest integer that's less than or equal to negative 0.5? It's not negative 0.5 because that's not an integer. And the integer that's less than negative 0.5 is negative 1. So when you're at negative 0.5, you're down 1. And that's how the steps are formed. So one thing that you'll need to be thinking about really when you do greatest integers is it's going to be steps. And then you need to think about it starts closed to open. Okay, closed to open. Different step functions can be reversed. Okay, but ours is always going to be closed open. Yeah, domain would basically be all real numbers, and range would be the set of integers. That's the only outputs you get are integer numbers. You never get decimals or fractions. So in order to answer that question, you could write the set of integers, or mathematicians have something called set builder notation, which you do not yet know.
So for the pink sheet, how do we know if it's an odd or even function?
For the pink sheet, I don't think that you necessarily have to do the odd or even tests because these are very simple functions. You can just look at it and tell by symmetry, and I'm okay by that.
Yeah, but this one's different. How do you know if this one's even or odd?
Oh, well, if you rotate it at 180 degrees, I think it will be neither because then if you think about rotating 180 degrees, your things will be flipped around. So it's going to be a neither. Okay. All right. So your homework assignment is here. These two are piecewise. So if you want to start a piecewise, you can start with 35 or 39, and then all of these are greatest integer. The 8 basic function sheet is due tomorrow, and also your quiz is due tomorrow. It does say your quiz is due today, but I thought it was due tomorrow yesterday, so that's what I said in class, so I'm holding to that, so you get an extra day if you need it. Okay. If you have your quiz corrections done and you want to turn them in, you certainly may. David, I'll get you yours here in just a second.